Record to the cloud. Okay. Now let me try to share screen and hope that everything goes okay. All right. Can you see my screen with the same handout I sent you all?
Yes.
Yeah.
Okay. So what I want to do though is go slowly over this. We've got plenty of time. And I want you to, interrupt, ask questions. I tried to pick 4 medical data sets that have some significance and that are freely available. The first one is just basically something that was published in December about basically lead exposure and their attempt to tie that into psychopathology in the US population over the last 75 years. Now, I'm not going to focus on the article. I'm going to focus on the fact that NHANES has lead levels, has for many years had blood lead levels, as well as cadmium and other heavy metals. And so I was interested, frankly, first I looked at adults because that's what I know more of. And also they've been around, if they're say 65 or older, they probably did get exposed to gasoline fumes that had lead as an additive. So sure enough, there were a lot of adults. Then I said, well, this article's, it deals with children. We have at least one pediatrician on board. So then I changed it to children, if you will. The first, let me go over NHANES a little bit, though. I love NHANES data because it's freely available, but I would consider there to be 3 drawbacks. One is it takes them a while to publish their results. So if you see something that's the 217 to 218 era, it may take them 3 years to get the results published that you can access everything. Second of all, that I'll address here in a second, is for whatever odd reason, instead of publishing it as an Excel file or or a CSV, it publishes an XPT file. And thirdly, it tends to wait. If they collect a bunch of patients, say 10,000 patients, and they said, we don't have enough Hispanic white patients, or whoever it happened to be, or non-Hispanic, Black, whatever, they will weight the data a little bit, and it requires a little bit of statistical know-how to take care of that weighting if you choose to publish this. If you're not publishing it, doesn't really make any difference. So those are the 3 drawbacks. Now, to convert NHANES data to CSV, there is a Windows package. That's what this link is. But what I've done, since I'm a Mac guy, is I have used, again, JASP that will convert XPT to CSV. I did a short video. That's what this QR code takes you to. And that will show you how to do it. It's really very easy. So in any case, my effort here on this first data set was pretty minimal. That is, I wanted to simply say, let's pull in the lead levels and let's pull in some demographics. That's a starting point. You all on your own could certainly merge a whole heck of a lot more data than that. But I wanted to do that. And also the other thing, you always have to know what the abbreviations stand for. Such as this one makes sense. It's gender, age, and years. F is ethnicity or race. EDU is education. Now, initially I had education for adults, but not for kids because you're not going to have any data if they're below the age 6 in all likelihood. But in any case, you do have to always know what these stand for. When I created for the 4th data set, I actually have a data dictionary I created that's available to explain what all of these are. So the family income to poverty ratio was part of demographics, and I included it simply because it makes sense that probably lead and pipes and you name it, industry is more likely in a poor neighborhood than a well-off neighborhood. And then the blood lead level, and it simply, I used the threshold that the CDC came up with, greater than 3.5, was of concern in children. So that's what I used. I think I've seen 5 micrograms per deciliter as well. So we'll go over some of the questions. I don't know. I hope some of you all made some attempt to work on these. And does anybody want to answer any of these questions and volunteer who's done this? Or do you want me to just keep talking? So, oops, let me admit another person here. Um, so we can go over uh, the orange workflow and then probably go back. Let's see. Oops, sorry. So I want to go over the workflow, first of all, of using the merge data widget. You start with a basic file. You open this up and you see it's demographics. I did skip education. I clicked on that. I did change ethnicity or race to categorical. Uh, Sometimes you'll run into this being a controversial factor. In other words, should you make it numerical, 1 through 4, or categorical? I think it should be categorical. Uh, Orange labeled it as numerical. I changed it. That's why you see it here as categorical. Once again, notice you can change it. So in any case, I changed it. Anytime you change anything, you have to hit apply. So that's demographics. Lead level is much easier. This is the lead level in micrograms per deciliter and the sequence number. Now, you don't need the sequence number for a model or a lot of other things, but to merge data, you do. So here, all you have to do is append columns. So this is adding a column to the right or left based on a sequence number in the 2 files. That's as simple as it is. But you can also concatenate tables. You could bring in data from 2 different eras. So instead of having 10,000 patients, you have 20,000 patients. And so you might say, well, yeah, I really like the demographic data and I like the blood lead levels, but I'd like to add other measures, you name it. Well, all you would have to do is add another merge here, right click and insert widget, add another merge, add another file here for whatever the lab work might be or the questionnaire or whatever, and you daisy chain these. You can keep daisy chaining them until you get all the data on there you want. But to make things a little bit easier, I want to open the data table, which is your way to take a quick look and say, was it successful? Do I see lead levels combined with demographics? Yep, there they are. But you should notice immediately, and there's another person coming in, should notice immediately that there's missing economic data and there's missing lead levels. Remember, the economic data is the family income to the poverty level. So if, and I'm not sure what 0 means, by the way, but in any case, the ones that are positive, like here's 1 of 5, 2 of 5, that means it's the family income is considerably more than the poverty level. So I like that as a barometer, but plenty of them are missing. Now, that's another is there a question? Okay. And so here, initially, I think on yours it may say age below 20 or something, but I said to myself, whoops, they don't draw a lead level until age 6. So then I went back in and I put age in years is between 6 and 20. So that's a little bit of a change, I think, compared to what I sent you in the email. But I want to just show you the workflow. So then I said, well, we got lots of missing data. If you, who knows what you would use, what you would connect to see which column has the amount of missing data and in what percent. We've already shown that in the data table, but what other widget could we insert here? Anybody know? The answer would be feature statistics, because each column, it'll tell you minimum, maximum, standard deviation, and any missing data. And you can always insert that anywhere here. And so we're going to opt to handle the missing data by the simplest technique, but probably the best in this situation. And that is, we're not going to put a random value in. We're not going to put the mean in. We're not going to put a distinct value for a missing lead level. We're going to try to make sense out of it. Now, let me comment that this data set's not a particularly good example. Last week was much better. When we had heart patients and there was a missing thallium, what this simple model-based decision tree did is it went in and it looked at the missing thallium, and it looked at this person's age, risk factors for heart disease, their performance on the treadmill, and labeled this person, the thallium, as normal. So it was an intelligent decision of the missing data. In the real world, you probably, with your team of researchers, would go over any missing data and make some decisions. What are you going to do about it? But for purposes of education, I'm using the best that I have, which is model-based imputation, which again is an educated guess of what the missing value should be, a calculated guess, as opposed to just using a random number or a mean. I hope that makes sense. And then once again, I put a data table there purely to confirm. I didn't have to do that. So here's the data table. I want to look and see, yep, not missing. The poverty to, or the family income to poverty levels there. So it's all there. So again, the point I want to make here also is, so these are going to be children, 6 to 20, the ones that got lead levels drawn. And then here's unmatched data, and you can, it's pretty much, if you check that, unmatched means these are not people aged 6 to 20. So these are, again, going to be the adults in here. And if you just look at the age and years, whoops, wait a minute. How can that be? Let's see. I'll have to figure that one out. That is not correct. I'll come back to that, but you should be able to do unmatched data here, and it would be everybody else if you would, and then you could do whatever with that and maintain a parallel workflow. So getting back to this, we might say, well, is there a correlation between age and lead level?
Dr. Hoyt,
Yeah.
sorry to interrupt you, but isn't that correct what it did? Because your parameters between 6 and 20, so it had young people and adults below 6
Oh,
and above
you're
6.
right. That is exactly what it is. Thank you. In other words, it's taking people below 6 and over 20. You're absolutely right. So that would be something. So what I showed you can't do. You'd have to go back here somewhere and split that off. So thank you. That's absolutely correct. And I changed this later when I realized that lead levels were drawn at age 6. The family income, by the way, is done at 0. So that's current. But no, that's a good observation. It made sense before when I didn't do it between 6 and 20. Okay, so but getting back to the scatter plot, is here on the y-axis is the lead level, on the x-axis is age. They bend it into age bins, but make a long story short, you look at the R value, it's hard to see as a minus 0.04, so there's no strong, in adults there clearly was. I don't remember, it was 0.2, I believe, that the older you were, the more likely you'd have an elevated lead level. This one, it caught my attention just because it's so high. Again, if you mouse over or you send it to a data table, you highlight it like this, send it to a data table or to the saved data, you can study this person. But going back to the mouse, it's a male, he's Mexican American, and the poverty level, income to poverty is very low. So this is somebody in a, again, most likely a very poor neighborhood. Uh, so you can go through these like that and look at different things. In this case, we looked at lead and race. They chose to automatically do an ANOVA for you and showed that it was that there was a difference. But notice the distribution here. When you look at the box plot, because they're outliers, it really is going to skew your data to a large degree. But you could do this. You could look at gender, and two is female, one is male. So it's higher in males than females and is statistically significant. This is a very tiny data set in terms of number of variables, but nonetheless wanted to show that. Uh, and then you can do correlation. Well, let me go violin plot here. There are definitely times when I think the violin plot is better for teaching. It may demonstrate outliers and other things better. The density dots you can simply unclick. If you want to see the actual data, you click that, the data points, but it makes it pretty clear about that. The box plot is, and you can't see it very well here, that introduces your interquartile range. Anything above the upper from here up tends to be an outlier. So those are all things that other types of bells and whistles that you can do. But there are times when I think the violin plot gives you a better demonstration of differences between groups, for instance. All right, so a couple of things. Number one, if you wanted to choose people, let's say, okay, we're going to establish that 3.5 micrograms per deciliter is the threshold. How would you then separate people out? Children with a level over 2.5, 3.5. How would you do that? What widget would you use? Anybody? You'd use your select rows because that's your filter. And so you could do select rows. Let me see if it, sometimes, yeah, it's chosen. I don't know why. Maybe because I'm trying to do a live demonstration. Let me see. Yeah, I mean, unfortunately, I'd have to restart this to have it show up to, so I'm not going to do that. Anytime Orange doesn't behave properly, you just save it, get out of it, and relaunch it, and it invariably works. But the point is, you would do select rows, like you would come back here, not there. You would you would put a new widget in there. You would do this, lead level is greater than, and you'd put 3.5. That's all you'd have to do here, connect it to the data table, send it to, you connect the select rows to a data table, and you'd see there's 14 children with elevated. And the correlations, again, this is such a small data set with number of variables. None of these are very significant. The sequence you don't need in there, you would get rid of. But this is just a demonstration. Anybody have ideas of what else they would add? If you wanted to study lead, what else would you add from NHANES data? Any ideas? I mean, lead can cause anemia, for instance. It can do, obviously, It can even cause dental abnormalities, lead lines. It definitely can cause some CNS problems, but I don't think NHANES gives enough information to make that very meaningful. So I'm going to go ahead and move on to the next one. So so again, to analyze adults, you would just simply go back earlier. You would not do it at age 6. You would do it over age 21 and above. All right, so let's talk about the diabetes prediction data set. This came from an ethnographic study in Virginia, not far from where Aaron is right now, south of Richmond in 2 counties. It's kind of a little bit of a strange study in a way because they simply went in, I guess, knocked on doors. These were all African American people living in a poor rural 2 counties, and basically took a lot of history, some blood work, some other exam data to look at risk factors for diabetes and heart disease. I could not find in the article, though, whether they knew whether these people were taking medications and whatnot, which would be obviously important if you're trying to make sense out of it. Now, I did modify the raw data by, number one, getting rid of some of the columns. For instance, they took blood pressures 2 or 3 times. I just went ahead and accepted the first one. Also, they did do hemoglobin A1C. So I just said simply if their level of A1C was 6.5 or higher, I labeled them 1 is diabetes, no is 0. That just gave us a target, if you will, something to do predictive analytics, which we could do next week when we get into classification. So is this classification or regression to predict diabetes? Anybody?
Regression.
Well, let's pull it up. So diabetes is yes or no categorical. So that's classification. But guess what? If you had the hemoglobin A1C in here, that's numerical. That would be regression. We'll go over this in a lot of detail next week, but that is one thing absolutely I want to drive home is when you talk about supervised learning, you're saying that I have a target. I know what I want to predict. In this case, it's diabetes, yes or no. It could be heart disease, yes or no. But if it's a number, you're trying to predict. Uh, I don't think you'd predict height, and I don't think you'd predict systolic blood pressure. But it could be a numerical value on here. Uh, that would be regression, and we'll give you a lot of different algorithms to do both classification and regression next week. All right, so
What
this
if
again,
BMI was a number? Well, BMI is a number, but what if you were trying to predict it based
you,
on height and weight?
you could. And so next week, remind us, let's go through multiple targets. So one of the points I want to make, if you have a very large data set that's new to you, several thousand patients, maybe 75, 100 variables, all odds are you can do both regression and classification on that data set and unsupervised learning. Let's say again, you have a lot of public health data with immunizations and zip codes and you name it. You might want to do unsupervised learning and look for clusters or patterns that you were not aware of. This all came to fore because of genomic data when they had SNPs or genetic abnormalities. They wanted to match up genomics with, genotypical abnormalities with phenotypical abnormalities. So that's unsupervised learning, which we will not cover, but in the intermediate course we would. That's fairly interesting topic, I might add. But you could predict any numerical thing theoretically by creating a regression. By the same token, you could predict, I don't think you would want to, I've never seen anybody predict gender, but you could. So anyway, you look in here, you see its target. So that would be what we're going to predict out of there. So just simply asking you all, and I think I asked this more than once, how would you approach this? You know, you're going to line these up. Which one would you look at first? Anybody? And if you saw Ferris Bueller Day Off, you would say Ferris. You know, you would ask who wants to volunteer? Which one would you want to look at first?
I like the scatter plot.
You could. I'll probably say that wouldn't be my first.
I like the box plot.
That's an awfully good one. I would probably, I'm going to say here are the top three, in my opinion. I won't say absolutely there have to be in that order. It's a little dogmatic, but I would say that my rule of thumb is always look at this first, because I had a friend, for instance, send me a data set, and he said, I don't understand. I can't create a model you know, he was using orange and so forth. And I looked at it initially and I went, yeah, that's pretty good. But then I scrolled down and then the trouble started. It had all kinds of errors that had text written across here. It was a nightmare, but not on the first page as you scroll down. But again, we can undo some of these. So to me, you can do it in the data table. I think it's even better in a spreadsheet, to be honest. And by the way, spreadsheets now have AI. I recently needed to manipulate data and I used Google Sheets and Gemini as part of it. So instead of me trying to figure out what formula to insert in what cell, I told Gemini that what I needed, it did it for me. I was pretty impressive. But the point is, I think the first thing is to look at your data and just see what it looks like. Be sure you understand it. And actually, let me go back and see if we still have BMI checked. Yeah. Just make it back a feature. Can't have two targets. All right, so I think data table is number one. And then it's a toss up here. I might argue feature statistics second, but I don't feel strongly about it. If you want to look at feature statistics based on whether they have diabetes or not, you can select that down here, or you can say, nah, let's just look at it as it is. You can do either. So, but the point is, you would look at these, number one, to look, you know, that's somewhat well distributed. Glucose not, because again, we'd have to look, there may be a threshold here is why it looks that way. The cholesterol is probably total cholesterol, and then the HDL to cholesterol ratio. You'd go down each one of those to look for anything that looked abnormal. And then a question here would be, how would you know how many diabetics you have versus non-diabetics? This is qualitative, if you will. That's gender. But you notice there's disparity. There's not many diabetics compared to non-diabetics based on hemoglobin A1C. So how would you tease that out? Which widget would really help? Anybody?
Can you repeat the question?
Yeah, in other words, so I showed you that there were a lot of non-diabetics in there, but how would you like to get the actual number? Quickly, easily, almost like cheating. The answer is, somebody mentioned box plot, but what you do, if that's your target, you find your target up here and you find your target down here, and wow, 330, 60. So that gives you to it quicker than any other way I know. You automatically get a chi-square. Obviously, huge difference between those two. But that is the easiest way to do it, honestly. Now you can also then you can make gender down here and diabetes and look at this, and is it different? No. So look at the chi-square, the p-value 0.8. So the percent of diabetics among men and women is about the same, if you will. You could look at, and again, in a data set, you would in point of fact, look at all of these. So cholesterol is different between in diabetics versus non-diabetics. Cholesterol is different. Glucose, that would be cheating. I mean, that it's going to be different. I would think the HDL to cholesterol ratio would be different because HDL is lower in diabetics than non-diabetics. Age, notice that diabetics, the mean is 58, non-diabetics 44. So the point is, this is a very valuable one to go back and forth looking at that. So we did that. And also, what widget would you look at minimum maximum for BMI? Again, feature statistics where let's open that up. Can you see that okay? Is that large enough?
Yes.
Okay. So you then, under BMI, let's see, that may be covered up. Let me get my face out of the way. Um, let's see, what do we
The
got?
sixth one, I think.
16 to 55. So that's believable. I mean, part of that's a reality check. You want to be sure that makes sense. What widgets would you use to see if glucose elevates with aging? Glucose is numerical, age is numerical. What would you use? Somebody mentioned that as
Scatter
a scatter plot. Exactly. So here's age and glucose, and you can do this different ways. Uh, Notice here that I show color regions. That's just a nice way to highlight the notice the glucose here of 200. So again, it's far from exact, but the point is, so you can color regions if you want to. We can undo that. You can also show regression lines. So again, so the red would be among people with diabetes, the blue would be without, and I assume uh, this gray would be in between. At least that's what I'm assuming. I don't think that's right because it's steeper. I'd have to figure out which one that is. But the point is, you could look for the relationship. You can also do correlation as well. So you can, again, remember to check the regression line if you're looking for a relationship to see how strong it is. All right, and then let's look at the violin plot. And again, we can do, let's do HDL cholesterol ratio and gender. I think there are times when this is a better visual display than a box plot. I would say they're complementary, if you will. And as I say, you can always put let's enlarge that. This is the interquartile range that's above here. So the ones that are above here are outliers, if you will. And we did that in week number 1. But I think it's a nice visual display of the distribution. And you could, again, look at distribution. You could do select rows for anything you want. You could select people that cholesterol is greater than such and so. And then correlations, if you did numerical, that's Pearson. So I happen to have BMI up. This is a little bit of common sense that it correlates highly with hip, weight, waist, height. But if there's some correlation here, it's negative with HDL cholesterol ratio, uh, diastolic blood pressure, there's correlation, uh, and so forth. So that gives you more information. And again, what correlates the highest with BMI? In this one, it's hip. I would have thought actually it would have been waist. But in any case, this is just the kind of things you would do early on exploring data. The term exploratory data analysis, EDA, is all about this. We've gone over it fairly quickly just for educational purposes. We're not spending a lot of time on any one aspect, but just for teaching purposes, say these are kind of the initial widgets as you want to learn more about your data set. Okay, now let's move on to the Framingham. This is a study that's been out there for a long time. Aaron, any idea how many years? Didn't it start like late 40s or 50s, I think?
Yeah, I think this was from there was a group at Harvard, I believe. I think that's
Yeah,
when they had,
that's right, it's Boston. And
yeah.
so this was one of the first ones, and I just use it for teaching purposes. I think they've already recognized problems with it. It's not perfect. But the point is, for teaching purposes, it's okay. So we're going to pull it up. We're going to once again focus on class imbalance. What did I say was the best way to determine the exact number of heart disease versus no heart disease? Box plot.
What?
Before we do that, though, I mean, I don't want to skip around, beat, uh, not in a logical sequence, but starting with this, let's look at the data first in the file widget. It says it's 4,240 instances, which means rows or patients, 16 features, which means the variables, predictors, or attributes. There's 1% missing value, so not much. Data has no target variable. Well, it actually does. We set it at the target as who developed 10 years of heart disease, yes or no. But so you've got heart rate, BMI, systolic, diastolic blood pressure, a little bit like the diabetic data set. Also, questionnaire, are you on blood pressure medicines, yes or no? Current smoker, yes or no? Number of cigarettes per day, some of the standard stuff, if you will. We'll hit apply to make sure everything's active. So getting back to the first widget, I would look at the data table to be sure that everything looks copacetic. And you can see there are missing values, for instance, for glucose, but not a whole lot. There's not a hemoglobin A1C because this was an early study. So again, I would look at the data table. And we already answered this, that I think race and education should actually be categorical. Some people would say education maybe should be ordinal. There's an order to it. That elementary school goes before, say, college and high school and intermediate school. But really and truly, there's some debate on that. But I'm going to say it's categorical. What widget would you look for class imbalance? The answer is box plot, where we use 10-year heart disease there. We used 10-year heart disease here. And so we have 3,596 people without heart disease, 644. The math works out that that's 15%, by the way. So 15% develop heart disease in that 10-year period of time. And actually, let's look at a couple other things. So what had the highest percent of missing values? You can look at the feature statistics. You can do it with this or you can do it without it. So you would scroll over and look at, see the missing, you go down, there's 2%, 1%, 1%, 9% under glucose. So glucose has the most missing, if you will. Let me go down and make sure that's correct. So that's how that's useful, if you will. Again, next week, we're going to be able just to kind of show you. Remember, I said that diabetes, heart disease here is going to be classification because it's categorical data. This is discrete data because it's either 0 or 1. It can't be 0.5. It can't be 1.5. Discrete data is categorical. It falls in a category. So that's classification. So what you could do, just so we'll go over next week, is you could create your test and score. Unfortunately, it's misbehaving. You do the test and score, you choose an algorithm like logistic regression, and you could predict it. Now, one other thing you can do here is you could look at, we already looked at the number or we can look at the number of people that claim to be diabetic also. And so there's 4,131 that claim they're not, and 109 claim they are diabetic. You can go in and also then look at everybody with a fasting blood sugar over 126 and see that they're close. The numbers are close. I won't belabor it. I think it was 85 people based on glucose and 109, I think it was, based on their questionnaire, do you or don't you have diabetes? So sometimes you can validate to see how close they are. But keep in mind, some people are going to be diabetic medicines and maybe their glucose is normal, maybe their hemoglobin A1C is normalized. So there's going to be somewhat of a disparity. Any questions on the Framingham? We'll mention this in more detail next week, but class imbalance is a reality. We'll show how it alters sensitivity and specificity. So it's a challenge. In the last data set is one that I created. You might say, well, why did I use this early one? Well, the answer was all the data was in and it covered a lot. It covered the outside activity, the lumens of light exposure they got, pulmonary function test, grip strength, you name it, cognitive testing. And so, you're free to use it any way you want to. I think it's a fun data set to play with. So here, we're only going to look at two scenarios in a way, such as what does grip strength correlate with? And cognitive testing, what does that correlate with? But there are lots of other things you could look at. And again, anybody want to, wax poetic about the importance of grip strength? As it's sort of overlooked as something you might test in the office. But what's the significance of grip strength? And actually, the number of sit-ups you can do, push-ups, pull-ups, the amount of weight you can lift to the dumbbell, barbell, it's all the same. It correlates. The nice thing about grip strength is it's been verified. We know exactly what the mean and standard deviation for men and women at ages are. But let's pull up and hopefully this active. It's not active. I will reopen it. So over here is just the NHANES data set. As you open it up, first of all, down here, there's some metadata, which means text, really. And we had some artificial names invented and used that are not real. Now, I did create, by the way, an extra column for diabetes, yes or no, based on their hemoglobin A1C. So it didn't come that way. I created it. So this could become a feature if you wanted it to turn it into classification. Let's go ahead. Whoops. Let's turn it into a target. There we are. Hit apply. So if we choose to try to predict the diabetes, yes or no, we can do it. And in here somewhere is the hemoglobin A1C. There's grip strength. Can anybody tell me why the forced vital capacity and grip strength are related?
Age?
I thought that was an interesting observation. Then it occurred to me that the answer is obvious. What do you base the forced vital capacity on? What is it dependent upon? Okay, age, height, and gender for forced vital capacity. Well, grip strength, age, height, and really, and gender. So the same variables, but what was interesting to me about the forced vital capacity is it requires some diaphragmatic strength and intercostal muscle strength. So it is a muscle test in a sense, plus motivation. If you're failing as you're getting older, you're probably not going to put out the muscle effort for any test, whether it's grip strength or whatever. But let's just start Let me see how we're doing with time. We're getting short on it. So I'm just simply saying we would do the same thing that we talked about throughout. It's sort of a broken record. We would go through all of this and recognize the good, the bad, and the ugly about our data, what we liked and the variables. But I would encourage you to look at it simply because I put a lot of interesting things in there. The insurance, their questionnaires, what they said they had, all their measurements, if you will, lab tests such as creatinine albumin or albumin to creatinine ratio rather. So all that lab work, iron levels, the CBC, there's serum creatinine levels to know if they got their primary smokers or secondary smoke. All this other stuff, average weekly activity, vitamin B levels, TSH, cognitive scores. So in any case, it's there for you to play with. The impute, we're going to, again, for teaching purposes, just say anything missing, we're going to try to impute it. And then you can select here where the gender is 1, here where the gender is 0. I hate that, sorry guys, we're zeros. And then you can basically look, in this case, we're going to look at correlations. So let's look at correlations in, this is the women as I recall. And I think it's fairly interesting. I already said height, age, notice the correlation with FVC, weight, BUN is interesting, and that's negative. I think that the stronger you are, the lower your BN and BUN, perhaps creatinine is. But as you go down this list, I think it's educational. One of the things I found as I went through this data, let me go down further if I can find it, was albumin and hemoglobin correlated with a lot of stuff that was positive for healthy people. It correlated with activity, a general sense of, when you did a questionnaire, do you consider yourself healthy, yes or no? Why is albumin and hemoglobin considered a health parameter? Anybody?
Nutrition?
What's that?
Maybe their nutrition levels are good. Because of that, they have high hemoglobin levels as well as albumin levels.
Well, I just think with chronic disease, all your organs start to shut down, including your bone marrow. And liver produces albumin. So the point is, in point of fact, with most chronic diseases, you see a slight ebbing of hemoglobin and albumin. So this is seen on both males and females. It wasn't that different. But, feel free to go through this. I think it is interesting because you can see income and education and so forth. I think there's one that made no sense, and I haven't gone back to figure it out. And that was something like general, and maybe it was only in women. I don't know. But it was something like general health was negatively correlated with grip strength. So I don't know what that means. But again, these are correlations, not causations. But as part of exploration, you'd look at it. By the same token, you would look at we'll look at cognition scores, 0 to 20, I think is the score. So we're looking at things that positively correlate with a higher cognitive score, education, general health. No, I'm sorry, it was this one. I don't know why general health had a negative correlation with cog score. You got me. Age, I understand. Income, I understand. But these are, again, simply correlations that get your attention or interesting, that most of them make sense, private insurance, grip strength and so forth. But this is just part of it. This was just your introduction to data. That's all I wanted to say about it. I'll stop it unless somebody has a question about this. I am exploring the idea of creating several large pediatric data sets, but it hadn't got off the ground using NHANES data, looking at some of these things. So let me just open it up. As I mentioned, Aaron and I will be discussing, let me turn the background light on. Aaron and I will be discussing more about whether we're going to definitely launch the intermediate course or not. We think that it would really, those of you who have done the beginning course, I think would get a lot out of it. Again, it would give you much more experience with data, and also we would introduce you to things that you don't normally experience, like Google Colab and a program that will analyze data with AI. So any comments next week? Again, just to review, it's largely about creating a classification model and a regression model. But the good news or the bad news is the first hour will be concepts. Once again, things like confusion matrix, receiver operator curve, they're all really important. What's overfitting, underfitting, you got to have it. It's just mandatory to go over that the first hour. The second hour will be with Orange, and that's the easy part, creating a classification or regression model. Any questions about that? So probably no later than Monday. Number one, I'll send you the recording from this session. Number two, I'll send you the handout about the concepts we'll go over. And three, I'll send you the Orange work files, if you will, for classification regression. Any questions? I haven't looked at the chat again. Let's see.
There was one question on imputation, I think, which I
Okay.
answered. Yeah.
Okay. And somebody answered the question 1948.
Mhm.
Yeah, that goes back in my era, I'm sorry to say. Okay, any other questions?
have
Or,
a
oh, by the
question.
ways,
Oh, go ahead.
You go ahead. Yeah.
Mine's just really, it's Ada. It's just a rather simple question. When you're using your distribution versus featured statistic widget, and it seems like the statistic widget are a bunch of different distributions, more or less. Yes?
yeah, they're bar graphs. I mean, that's a good point. We didn't emphasize that very much. It is really nothing but bar graphs, particularly of categorical data. So I do both. To be honest, I will look at feature statistics, look for missing data more than anything else. But I will look at minimum maximum to see what the population looks like. But if I want to look for outliers, for instance, I will look at, the box plot, the violin plot, and the distributions, if you will. But that's a good point. And I didn't do a good job of pointing out the difference between a bar graph and a histogram. Histogram, the bars will be touching. Bar graph, for categorical data, they're not touching. So we can point that out next week as well. That's a good question. Any other questions?
I have a question. So when you have like for enhanced data, there are like multiple years which are separated with each other. So when you use Orange to analyze enhanced data, like are you going to pull the weights from the database and run it, or like how do you do, like are you going to analyze them separately for the each year?
Am I going to analyze the data separately for each year?
I mean, like in Enhance, you have like 2 year database, like it's like 2 years together for each data set. So if
Yes.
you want to combine them, you have to weight them. So are you going to like do it when you use Orange? How do you do that? Like you pull the data from them?
Oh,
and
well,
combine
no, you can combine.
Uh-huh.
So that's going to be called concatenate or concatenation, as opposed to what I showed you merging is really putting a column, adding a column to your existing database. But the answer is you can do what I think you're hinting at. You can say, take 10,000 patients from a 2-year period, say 2015 to 2016, and you then can combine it with another data era. So now you've got 20,000 patients.
Oh,
So
okay.
you can do that using Orange. I've not done that. You certainly can. You have to be a little bit careful because remember that in Orange, sometimes they, in a given era, they may have tested things like audiograms, but 2 years later, they're no longer testing
Yeah, that
audiograms.
I have seen that, yeah, even for the cognitive data, it's not only available for 2 years. Afterwards, it's not there.
Yeah, so the point is, you can do it, but you may have holes in the data. There may be missing data when you combine different eras. So that's the only problem. But that's why I like the 2017 to 21 data set because they combine 2 eras. There's 15,000 patients in that data period. They did that prior to COVID. So if you're
Yes.
looking for a big data set that's bigger than the other 2-year periods, try that
That's
one.
it.
2017 to 2020, I think it is.
Yeah, afterwards, it's not there. Yeah.
Yeah, that gives you the most patients. Any other questions? Okay, if not, thank you for your participation, and then I would be back in touch with you about week 4 and also about whether we're going to launch the intermediate course, yes or no. Okay? Otherwise, have a wonderful weekend that I hope is free of snow and freezing weather. All right, take care. Bye-bye, you all.
Thank you.
Thank you.
Okay.
Thank you.